All right, so now we're recording, started in process. Okay, so I want to do a Mentimeter. I had it ready to where we could play around with some of this stuff because we did technically cover everything that we needed to go for this unit. So let's do a Mentimeter. Let's play around with it, see where we're at, and yeah, let's just have some fun today. And then we'll go over the last little part of this unit, and then we'll finish up. So let me switch over real quick. So we're going over Newton's law. So I got a number of questions to kind of bring it all home. So first, join the Mentimeter. I'll put the code in the chat too. It'll be mostly just this unit. I'll put it in there just in case. All right, let me go to, let's start going. This one probably, this will probably take us to 6. All right. So just to get started, inertia is the tendency of an object to resist change in its state of motion, stubborn act of will to keep doing whatever the object is doing, or the tendency of an object to resist change in its velocity, or the tendency of object to resist acceleration. So this was not a trick question. The answer is all of the above. So these are just different ways to represent what inertia is. And we get that from, the practice problems where they have the definitions. So the amount of inertia possessed by an object is solely dependent upon its mass or velocity. So good, 100% correct. Good job, good job. The amount of inertia possessed by an object is solely dependent upon its mass. You talked about that when we went through the work a little bit earlier. The unit for mass is what? Kilograms or newtons? The unit for mass, kilograms or newtons? Kilograms, good job, good job. The unit for force is kilograms or newtons? Newtons, good job, 100%, good job, good job, good job. Unit for force is newtons. If the force acting on an object are balanced, the object will what? Maintain a state of motion or accelerate? Maintain the state of motion, good job, 100%. When the forces acting on an object are balanced, we call this state equilibrium or acceleration. Equilibrium, good job. 100% again. When the forces acting on an object are unbalanced, this causes, we say equilibrium or acceleration. Causes acceleration, good. The net force is the vector sum of all the individual forces acting upon an object, or the vector sum of all the individual accelerations act upon an object? Individual forces. Makes sense, net force. Sum of all the individual forces. Good job. When the forces are balanced, we say the net force is equal to 0 or the mass of the object times its acceleration. When the forces are balanced, we say the net force is equal to what? Which one? 0. When the forces are balanced, we say the net force is equal to 0, which means whatever we see on one side, we see on the other side. Like if we see our free body diagram, up is equal to down, left is equal to right. When the forces are unbalanced, we say the net force is equal to 0 or mass of the object times acceleration. Good. Mass of the object times acceleration. So when the forces are balanced, we say the net force is equal to 0, but that's the state of equilibrium. But when the forces are unbalanced, we see that we cause acceleration. So now that we have that, we can say that the net force is equal to the mass of the object times acceleration. What is Newton's first law? An object in rest will stay at rest, an object in motion will stay in motion unless impacted by an unbalanced force. To be honest with you, it's the whole thing. So I hope you read it all the way through. That's the entire first law. An object in rest will stay at rest, an object in motion will stay in motion unless enacted upon by an unbalanced force. If you read it like that or say it like that, you'll really understand it. Because now that brings us into, I believe, Newton's second law. What is Newton's second law? When forces are imbalanced, the net force is equal to the mass of the object times the acceleration of the object. Pretty much the same thing. When forces are unbalanced, the net force is equal to the mass of the object times the acceleration of the object. What type of diagram do we use to represent forces acting upon an object? A free body diagram or a dot diagram? Good, a free body diagram. What force is the force at which the Earth, Moon, or other massively large objects attracts other objects towards itself? Weight or the force of gravity? Basically the same answer. We say do force due to gravity, but we also calculate that same as weight. So either one is fine. What is the acceleration due to gravity on Earth? 9.8 meters per second squared or 1.62 meters per second squared? 100% correct. Good job. 9.8 meters per second squared. What is acceleration due to gravity on the moon? 9.8 or 1.62 meters per second squared? 1.62. Now you don't need to know that by heart, but it's to show you that just on different places, like the moon and the Earth, gravity is different. Acceleration due to gravity is different. What force is exerted by a spring upon the objects connected to each of its two ends? We got normal force, spring, friction, air resistance, tension, applied force. Which one is exerted by a spring? Spring force. Makes sense, right? When you have a spring, the force that causes it to be connected with the two ends, spring in there. That's why we have the spring constant, all that in there. What force is applied to an object by a person or another object? What force is applied to an object by a person or another object? Applied force. Applied force. It's in the definition. Applied force. Applied push, pull from one person or object or by person to an object by a person to another object. That's applied force. What force is transmitted through a string, rope, wire, or cable when it's pulled tight by forces acting from each end? String, rope, wire, or cable. Tension. Good. Tension. Anytime we think about string, rope, wire, or cable, you should automatically think tension because think about like tension, tension in the rope, tension in the string, tension. You heard that phrase before. That's literally the tension force. What force is a special type of frictional force that acts upon objects as they travel through the air? What force is a special type of frictional force which acts upon objects as they travel through the air? Air resistance. Now, friction is almost there. What we're talking about right now is as they travel through the air. So we're specific on the air. Specific on the air right now is the medium that we're going through. So air resistance. What force is exerted by a surface as an object moves across it? What force is exerted by a surface as an object moves across it? It's got to be on a surface, and then you're moving across it. You feel this force? Friction, right? So now we talk about normal force that's exerted by the surface on top of the object, like while we're there, right? But what force is exerted by surface as it moves across, right? So friction as it slides across, it rolls across. That's when we start to see the frictional force because it works against it. And here's a key word for this one, right? What force is the support force exerted upon an object when it is in contact with another stable object? Think about the word support, support, to support the object. Yes, good, 100%. Normal force. Normal force is what supports the object as it's sitting on like a counter or a table or on the ground. So it doesn't just fly off into space. You want to now identify the different types of friction, right? What different types of frictions did I cover and talk about? We have static friction, sliding friction, rolling friction. Which one is the different types of friction? Good, all three, right? Static friction, just you holding it, then sliding friction as it's going across, and then rolling friction. So there's three different types of frictions we talked about. What does this standard symbol stand for? This mu, the coefficient of tension or the coefficient of friction? Good, the coefficient of friction. Frictional force equal to what? Mu times the normal force or mu times the tension force? Close. So now mu times the frictional force. You almost got the mu times the normal force. You almost got 100%. That coefficient of friction multiplied by the normal force, which is the support force to keep it on the surface. That's what we have to create the frictional force. What are the units for mu? Newtons, kilograms, meters per second square, or no units? Actually, no units. There's no units for the coefficient of friction. If we were to do a kind of some math calculation, right, where we found mu based off of the frictional force and the normal force, we would see that the units actually cancel out. So that's where we get this no units from. Forces come in what? Pairs or triples? Yes, forces come in pairs. Now, knowing that forces come in pairs, what is an action force? The initial force exerted on the second object, or the equal force exerted on the first object, but in the opposite direction? So the action force is the initial force. So it's like the action verb, right? What am I doing? That's the initial thing that's being done. So we got the action. Now, what is the reaction force? Is it the initial force exerted on the second object, or is the equal force exerted on the first object in the opposite direction? 100%. It's the equal force exerted on the first object, but in the opposite direction. Now, we're understanding that with action force and reaction force. What is Newton's third law? For every action, there is an equal and opposite reaction. That is Newton's third laws altogether. Now, here's just a question I just need to know. Are you learning physics? Type your answer in. So much physics. That's hilarious. Sure. Yes, I got one wrong. The correct answer was yes. I just had to make a correct answer. I just really wanted to know what y'all were learning. So we got our leaderboard. Let's see who won today. Who was the hustler? That was you. Victory. Congrats. FC, and who's FC?
That's me. That's Courtney.
Courtney. Okay, good. Came in second place. Good job. Lakshmi came in third. Is that you?
Yeah, that's me.
All right, good. Congrats to you guys. Top three. Good job. I wanted to make it a little fun today, but I had to make sure that we covered everything before I could really start doing the Mentimeter. But guys did a good job. And it seems like you actually did catch on to a little of the vocab stuff, even though I was wondering how you guys were doing, with missing classes and stuff I had. But you guys did a good job. So let's keep the train moving because we're right at 6. So I see how we can get. Oh, we're right into. Okay,
I have a question.
Go ahead.
Are we going over the stuff that's on the midterm, or are we going over stuff that's on a whole nother unit?
No, this is the same thing. This is the same unit too. I'm finishing it today.
Okay.
No midterm too.
The
We have no
midterm
midterm
again?
exam. No midterm exam.
Oh, because
All right. So when we first started this, right, I introduced our end goal, right? This is what we're trying to get to be able to solve this type of problem, right? During a football workout, 2 linemen are pushing the coach on a sled. The combined mass of the sled and the coach is 300 kilograms. The coefficient of friction between the sled and the grass is 0.8. The sled accelerates at a rate of 0.5 .80 meters per second. Determine the force applied to the sled by the lineman, right? So then we went through all of these topics. I think we're at the very last one, which is Newton's second law in problem solving, to be able to solve this type of problem, right? We first established Newton's laws. The first law, an object at rest will stay at rest, and an object in motion will stay in motion unless impacted by unbalanced force. When forces are unbalanced, the net force is equal to the mass of the object times the acceleration of the object. And then the third law, for every action, there is an equal opposite reaction. But I took my time in breaking it down. We talked about inertia. The tendency of an object to resist change in the state of motion is dependent solely upon its mass. We've seen that as well. And we went into some preconceptions between forces and motion. And then we really identified what a force is, right? It's a vector quantity, a push or a pull. We have contact forces, which occur to physical contact, action at distant forces without physical contact. And we use free body diagrams to represent them. And then they come in pairs. And then the sum of the net force is the individual sum of all the acting forces on the object. That brings us to talking about balanced forces. Object in motion will stay in motion if the forces are balanced. We call that equilibrium. Net force is equal to 0. Balanced forces, the object is balanced. The object will stay in motion. But when it's unbalanced, the state will cause acceleration. The net force is equal to the mass times acceleration when it's unbalanced. And you could even tell, like we did this with the graphs, right? We see unbalanced forces when we see acceleration present, which means we see a change in our velocity. When we see no change in our velocity, that means that it's constant. No, there's no acceleration, which means that we're at a constant velocity, which means that there are balanced forces. And this is key because this is what we've seen in the first unit, right? So this is taking what we've seen in the first unit and bringing it now into the second unit to forces and why it matters. Yeah, and pretty much that when we get down to it, understanding balanced forces in first law, basically, the sum of the forces is equal to 0 because the object in motion stays in motion. And then we get into the second law. The forces are unbalanced. So now we have the sum of the forces equal to mass times acceleration. And we just kind of spam that through, right? We talked about some different types of forces here, different things with forces, and recognizing the different forces. We did some more preconception stuff between mass and weight as well. Your mass is different from your weight. Weight is actually the force due to gravity, so it's a force in newtons, while your mass is actually measured in kilograms, and it never changes, right? So weight changes as we go in different places, like Earth, or we go on the moon. Then we get into Newton's second law. We looked at their acceleration. I remember this one, yeah. Trying to think, that force acceleration. Looking at this one relating it to velocity time graphs that we've seen before as well, too, to kind of be able to talk about that motion. Then we started getting into free body diagrams, right? When we got into free body diagrams, this is how we design and say, okay, we have a problem. Now let's see all the forces acting on that problem so that we could be able to solve it. And then once you have a free body diagram, you can throw some numbers in there and be able to find different quantities, find an acceleration, find a mass, find a force. It's not already given to you, just off of a picture, right? We played around with that. We did the sled example and we did a car example. And then we kept spamming that to where we just kept looking at different types of free body diagrams and finding the values out of it, right? We talked a little bit about friction, right? And friction is important too because friction is very much applied in all different types of scenarios, right? And it's mu times the normal force. Mu times the normal force. I said it's equal to the coefficient of friction. I didn't put times the normal force, so that's a typo on my bad. But it's mu times the normal force. And when we went this one right here, we had to play around with finding friction if the acceleration is 0, right? So it shows us that we're actually in a state of equilibrium because there's no acceleration present, which means that the forces are balanced. And with the forces being balanced, that means that the friction must be equal to the applied force, 10, 10. And then when we're doing that, because we know friction is equal to mu times the normal force, we know that mu, we could find mu by dividing frictional force by the normal force. So there we get 0.83. And the coefficient of friction, just so you always know, right? It should always be between 0 and 1. It should not be less than 0, and it should not be bigger than 1. Then we're understanding friction, right? Remember, it talked about how air resistance is like friction in the air. Now we can understand how air resistance work a little bit by taking that same principle, right? As we travel down, we skydive, the air resistance gets a little bit bigger until we get to a certain point to where at the end where it reaches terminal velocity. That's when the air resistance, it matches with the gravity and we're in a state of equilibrium, which means you're not accelerating anymore. So in this diagram, we talked about it too. There was two places where you hit terminal velocity. The first one is when you are just falling in the air and your air resistance matches your weight, and that's without the parachute. And the second one is when the parachute matches with the force due to gravity or your weight, and you actually are trying to slow down, and now you hit that same velocity to where you don't change in there. So those are 2 times where you're skydiving and you hit terminal velocity. The other times you're either slowing down or accelerating. So in the top, you're accelerating because you don't have the parachute, so you're just going ahead, gravity's pulling you down, you're getting faster, 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 faster. The second one, you have air resistance pulling you up because it's counteracting gravity, so now you're going slower, 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 slower. Then we did some preconceptions pretty much to end it up with the elephant and the feather. And we wanted to identify each statement as true. And then we kind of figured out that certain things about that we thought about were air resistance, and without air resistance, we were kind of wrong. Then that brings us to our, I think, our last points of understanding action and reaction forces. So now we have an action force, the initial force exerted on the second object, where the reaction force is the equal force exerted on the first object, but in the opposite direction. So we get Newton's third law. For every action, there is an equal and opposite reaction or action. Like this one, right? Athlete's hands pushes the medicine ball forward. The medicine ball pushes the athlete's hands backwards. That type of thing. But where does this really come into play at is when we go back and forth for understanding how, just like first and second law went together, we understand how second and third law goes together. So when a bullet is loaded into a rifle and the trigger is pulled, the force exerted on one by the bullet is equal to the force exerted by the rifle. So that's the same amount of force that's exerted to the bullet by the bullet. The experience by the bullet is the same force experienced by the rifle, right? But what differs, right? The resulting acceleration of the bullet is greater than the resulting acceleration of the rifle. And like, think about it. Some of the forces equal to mass times acceleration, right? Because there is an acceleration present, there's going to be Newton's second law to where now we have force, we're going to be unbalanced force, we're going to have acceleration. So now we see that the acceleration is going to change because with those two objects, they have a different mass, right? The sum of the forces, right? The force between what's felt by the bullet and also what's felt by the rifle is the same force, but their masses are different. Therefore, their accelerations will also differ as well. So the least massive object is going to have the higher acceleration, right? In that scenario. And then we just bring it back home to understand the laws again. The object in rest will stay at rest, and the object in motion will stay in motion unless acted by a balanced force. When the forces are unbalanced, the net force is equal to the mass of the object times the acceleration of the object. Then we got third law. Okay. When the third law says for every action, there is an equal and opposite reaction. Now, I covered that in about 8 minutes to review pretty much this whole unit, what we got, just to get to this very last part, which was Newton's second law and understanding that with problem solving, right? Now, let's go to, give me a second. All right, so on the very last page of the packet, right, this is question number 5. So I picked this one to warm them up for the last one that we had, right? So it says a basketball star exerts a force of 3,225 average value upon the gym floor, newtons, in order to accelerate his 76.5 kilogram body upward. Determine the acceleration of the player. Determine the speed of the player if the force endures for a time of 0.15 seconds. So one moment. Like I said, I am in person. I also have Victory and Sean, right?
Oh no, I'm on my way. I just got off the train.
Okay, so Courtney's on her way too. Sean, right? Yeah, I got Victory and Sean and Courtney on her way. So as I'm doing this, I'm going to, yes, 5 on the last page. We're going to do the same thing as what we did last class. I'll have one of them come up here. I'll turn my camera on so you can see. One of them come up here. give me the free body diagram, but we'll talk it through, and we'll solve the problem. So we'll do the free body diagram, and we'll kind of walk it through. So we'll do it together. Actually, I'll let you both work together. So give me the free body diagram and solve it. So I need a free body diagram. Let's talk through it. So first, what's going on?
He's jumping, moving his body up, or he's jumping.
Let me know if you could see Sean right on the board, or if you need me to move the camera. A very intricate free body diagram. So as you join this free body diagram, tell us what forces you believe are present.
I believe applied force and gravity force are present.
Okay.
He's applying force to his legs and his feet to break the pull of gravity and jump.
Okay.
I think, and I feel like the F applied has to be bigger than the F grav because he needs to actually break the strength of gravity.
Okay. So does this person, basketball star like Michael Jordan, does he get off the ground?
I don't know. It says upward, but I'm not sure. Yeah.
So
Yes.
he gets off the ground.
Yeah, he gets off the ground.
So now with this person get off the ground, victory, are the forces balanced or unbalanced?
They're
Unbalanced.
Unbalanced, because now if he's getting off the ground, what does that mean?
It's off.
He's accelerating.
Speed and acceleration.
Speed and acceleration, but also what does that tell us about our free body diagram?
That it won't equal zero. The sum won't be zero.
The sum won't be zero, so how do we represent that in our free body diagram?
I forgot. What do you mean? How do we represent it?
How do you draw the picture so I know? Because right now them arrows look equal to me.
They look equal. They're not equal.
The bottom one is
The bottom
smaller.
one is shorter. Because they're not equal.
Maybe the units, putting units with that.
I mean, you could put units, but just make the top one bigger. Like exaggerate it. But do you understand the concept that when the force is unbalanced, that means one force is
One
bigger
force
than
is
the
bigger than the other. Yes.
other?
They're easier to see.
Yes, that's right.
Yeah.
So now what's knowing that, right? Because we have unbalanced forces, the sum of the forces is equal to what?
Acceleration.
Some of the forces are equal to mass.
Right.
What you just said.
Oh.
E F is equal to MA. M times A.
Now it's knowing that, right? What would be the sum of the forces?
Wait,
It say 300.
it says
3,225.
3,225 normal force. Or
Normal
just
force?
force. It's force. That's his applied force. That's the upward force.
That's the upwards.
Before you look at the numbers, right? So think about it. If you have one force bigger than the other, remember I called it earlier last class, you have a W word.
Wait.
Wait.
No, W word. When you are scoring a lot of points in a game,
Winning.
you're
Oh, wait.
winner, and you have a winner, you gotta
You're
have
loser.
a loser.
Oh.
Yeah.
So which force is winning and which force is losing?
The applied force upward. the
So
upward
usually
force.
when I do this, I put like right underneath that equation, I put W minus L. So I do W minus L equals mass times acceleration. So now I know I'm looking for the winner and the loser, because that'll tell me which order to put it in when I do my sum, right? So which one is winning?
The applied force.
So instead of W, you put
Applied force.
F,
F.
applied.
F-A-A-P-P.
And then now for the loser, what do you have?
F graph.
So now you have organized to where now you have your winner and you have your loser, right? And that's equal to mass times acceleration. Now are we able to start putting some numbers in?
Yes.
Did they give us numbers?
They gave
I gotta
us
reread this.
3,225
It says the average value. What does that mean?
That's
Math.
fine. That's the average of force that he applied. Like, you know, if you like if you jump, like if you do like a
There's a
force plate,
certain range.
it's a range. Like
yeah.
it might be like a little bit less. So they're just saying the average force.
Mhm.
We have his mass, which is 76.5 kilograms.
So start following that.
And the acceleration would be gravity, correct?
Is acceleration gravity?
There's nothing else accelerating it, so yeah. All right.
Let's think about it, right? If gravity is pulling him down, sorry, if he's jumping against gravity, right, and gravity is pulling him down 9.8, would that still be the same acceleration, or would it be something different? But think about it, right? For him to get off the ground, right,
He'd have to be moving faster than 9.8. Or he'd
and then in what direction?
upwards. He'd have to be accelerating 9.8 meters a second upwards. More than 9.8 meters a second upwards.
So do we even know what that is?
Mhm.
So right now it should
It's
still
just
be
a
A.
F graph.
So now, taking us back to 7th grade, you're trying to solve this equation, but you have two unknowns. Can you solve this equation with two unknowns?
No.
So we have to find
Well, at least one more factor.
one
At least
more, right?
more variable.
What one can we find based off what we know? Can we find acceleration right now?
No,
Can we find F gravity?
you can possibly find F gravity.
Because F gravity is what?
It's the
Wait,
same. 9.8.
Because what is it?
9.8.
But what is F gravity?
it's not that.
Gravity.
It's
The force due to gravity, but what is it? It's also called, it's what?
Newton's
Acceleration.
acceleration.
Well, that won't work because
Well, hold on, slow down. The alternate word for force due to gravity is also what?
weight.
Yes.
Weight.
So what's the weight of that object? The person.
76.5
Kilogram.
kilograms.
Is the
Wait, and you do that.
hold on, slow down. You still say the word, slow down. 76.5 kilograms is the what of the object, the person?
It's the mass of the
The mass. So how do I find this person's force due to gravity or its weight?
You put it over 9.8. You put his mass over 9.8.
Mass over 9.8?
Or is it gravity over mass? Or mass over gravity?
Think about it. Don't go too fast.
Mass
Say it out
times
loud.
gravity
Mass times gravity, because gravity is a what?
Oh, mass times.
is force.
It's
Gravity.
an acceleration. It's a weight.
Yes.
Okay.
Wait, hold on. Gravity is a what?
Acceleration.
Acceleration. Now the force due to gravity, that is a force. And that's also called
The weight.
weight. Yes. So to find the weight, we have to multiply objects
Mass
Mass
times
times-
or acceleration of gravity.
acceleration due to gravity, which is what?
It's 9.8.
So can we find F grav?
76.5. It's my calculator.
There we go.
I got 749.7.
Okay. So now rewrite the entire equation now with the including new F gravity.
If we do 3,225 minus 749.7, we get and then for this, to get it over on this side, I divide 7.6, correct?
Go ahead.
over 7.
There you go. What is that?
See. 2475. I got 32.36 approximate.
Okay, 32.36, right? Meters per second squared. Make sure we say
Wait,
that.
wait. You right. Yeah.
Now the numbers could be wrong, but I'll check it. We'll check it in a second. But I like the way that we went through the process and how we talked through it, right? Now, we're not done. Hold on. So now we got the second part, right? Now, this problem sounds similar to what problem that we solved last unit.
I was gone for 3 weeks. Don't ask me.
The final problem that was on the
Oh, Michael Jordan.
the Michael Jordan problem, right? So it's the same thing, right? And we use what to solve the Michael Jordan problem?
You
Remember the equations? What were they called?
kinematic equation.
Kinematic equations, right? So how does what we did in the first unit relate to what we're learning now, right? Because it seems like, to be honest with you, it could be disjointed. But I told you at the very end of the unit, the most important concept that you would take from that first unit was acceleration. Acceleration is also what?
A vector
It is a vector. In its definition, acceleration is the
change
And-
in velocity over time.
over time, right? So now let's think about that, right? They tell us in the second part, they say, determine the follow speed of the player if the force endures for a time of 0.15 seconds, right? Now, there's two ways to go about it, right? They said they want the final speed, right? So if they want this final speed, first speed is a what?
Speed is it's a scalar and it's measured in over distance, total distance.
It's fine, right? So do they really care about the direction when it comes to they saying the final? So they
They
don't
don't
really
care
want
about
the
it.
velocity. They just want the final speed. They just want the quantity, right? So now with that, right? We know that we just need to find out what the final speed is at the end of the motion, right? Now, let's think about this. How do I say this?
This is the one that I really don't understand. The type of problem.
This one?
I couldn't really see that clear out can right here.
Oh, yeah. So we just found acceleration, which was just pretty much set it up, do a winner minus loser, and then we find acceleration by dividing by the mass.
What problem are we on again? Number 5?
We're on
Five
number
on
five
the
at
very
back.
last one.
Yeah, right. This one, right?
Mhm.
Yeah.
All right.
So now we found acceleration, but now let's relate it to what we learned in the first semester, right? Not first semester. First unit. Say acceleration one more time.
Acceleration is a change in velocity over time.
Now write it on the board.
Oh.
But write it with letters.
Write it with letters. Okay.
Get rid of that the delta for the A.
Delta.
All right, so acceleration is equal to the change of velocity over time, right? Now, what does change of velocity?
Change in velocity, the rate at which it is occurring has changed.
Rate that changes over time. That thing.
That was position, but that was close. But change of velocity. Think about it. If something has to change, that means it has to have a what?
Speed.
That's the rate.
No, acceleration.
If it's changing, wait, no, just anything changes, right?
It
How
has
do you
to have
measure
a
change?
Magnitude.
How do you measure change?
Over time.
I just know it's a triangle. Is it distance or displacement?
Hold on, you're just saying words. Think about it. How do you measure change? Not just over time, but just how do you measure change?
With numerical.
Oh, whenever it stops.
Stops from when it
Starts.
starts. So that means it has to have a
Initial and a final.
exactly. So now we have initial velocity and we have a
Final velocity.
final velocity. So now there's change in velocity. And how do you measure change? You measure from the say it again. Start to the finish, or you could do it the other way where you do from the
Finish to start.
To the next stop,
yes. So like from the finish to the
to the next.
Okay, that's
stop.
good.
or from where you started from, like where you finished to where you.
Cause I thought
Sorry.
sometimes in some of the equations, like on some of them, this is what you say, at least this is the way I program it. When you start right there and you stop right here, the first one doesn't count. You don't start counting it until you stop right here.
No, that was that one
That
problem.
was displaced.
That was that one problem with the stopwatch. Yeah, they told you to do that on purpose. So now this one right here, right? So if I was to start where Sean is and walk to you, right? To find my distance, I have to figure out how far from where you are Sean was. So now I would do where you're at minus,
Where he is.
yes.
So
So
it's initial velocity minus final velocity.
But you
Final
can
velocity minus
but you can
Yes.
rearrange it depending on the values. Certain, depending on position, you can have a negative position.
that is true. But generally, think about it as what you just
When
said.
it's negative, it's always to the left.
Hold on, no, don't generalize it.
Don't generalize it.
Just go with what we just said.
Okay,
You
So
can have
change of velocity is equal to what you said earlier,
final velocity minus initial.
right there.
I wrote it back. VF instead. And that's equal to acceleration.
Yes.
Acceleration equal to.
I just have a question.
Go ahead.
Why are we doing it this way? Like, since we have
Hold on,
the
hold on.
acceleration-
No. I just started with this way. If you want to pick a different way, just hold it. I'll come right back to you because I know it's another way you
Oh,
can do
okay.
it.
Got it.
Yes. Now, it's still because change of velocity is equal to final velocity minus initial
Is
velocity.
this the average velocity?
No, that's just the change of
This is the
velocity.
change in velocity. Okay.
But acceleration is equal to what?
Change in velocity over time.
So now acceleration is equal to the final velocity minus initial velocity.
Over final velocity minus initial velocity over T1 and T2.
Time, just time.
Just time. Okay, just time.
No, put delta T. But you don't have to break it down as T1 and T2.
Okay.
We have the interval.
Is that a 9? Is that 749.7?
74947. Yeah.
Oh, okay. I didn't know what that was.
My handwriting's bad.
Okay, so now we have that bottom one, right? Which we know, right? Now let's think about it. Plug in some numbers real quick.
I'm so lost.
Wait, so
Just know that the acceleration is that right there. And once you get over here, you're gonna just plug in the numbers. Matter of fact, use a different color.
okay.
Anytime you plug in a number, put it in green. Anytime you don't have a number, leave it in black.
Okay, so my acceleration is 32.6. Equal to velocity final. Okay, now I'm confused now. Wait. I know the time.
So write it in green.
Can you move the laptop slightly to the okay,
Wait,
not that much. Not that much.
Put in the numbers. Other way?
This is,
Which way?
Yeah, okay, that's good.
0.15.
We got numbers. We plugging them in. Oh, put that in green. Put that in green. Put that
Oh,
in
my
green.
bad.
But that's what we know. We're gonna leave the unknown ones in black.
Good, I messed up right now. 0.150 seconds.
All right. What we
So
don't
we-
know, we put it in black.
I don't understand what's going on.
You just put it in
We're
the second
doing
part.
this one right here.
It's the same problem.
This is a whole nother part.
This is the
Yeah.
same
Read
problem.
the part, the second part. The second part they asked about the time.
Determine the final speed.
Okay, and then I don't think we know the velocities. We don't.
We don't. So leave them in black.
B. Yeah. Fine.
Same thing we did earlier, right? Can we solve that equation with two unknowns?
No, we cannot. We need one more variable.
Can I ask a question? I'm
Right.
gonna read it again. Oh, so it would be the time,
That's the time. The,
which is, so. what's-
0.1.
what would be the final velocity then?
We have to find it.
we have to find that.
Okay,
But can we find it if we don't know the initial velocity?
We can find it if we don't know the initial velocity. We need the final velocity, I think, more, right?
No, we need to find a velocity, but can we find it if we don't know the initial
Oh,
velocity?
no, we can't. We need the initial velocity first.
Now, let's think about it. Do we know the initial velocity?
We don't.
Can we find out what it is?
We can't. We'll know that at least the time at initial velocity will be 0.
Why do you say that?
Because we haven't begun to move. That's our starting position.
So you're doing what?
Assuming.
Assuming, there we go.
Mhm.
We should have did this at the beginning. Write the words given, assume, and unknown. See, I messed up. See, I messed up. I know Carrie's online. My fault. I didn't start with the given, assumed, and unknown. All right. So let's take a step back, right? In red, right here. We were given what?
We were given the
time,
we were given time, we were given mass, and we were given force.
Right, all of that.
the weight newtons,
We calculated that
so we don't count that.
because it
That's not
wasn't
what was
given
given
to us.
initially. Time, mass, and some force.
And our unknown we tried to find is the what?
Is
Final
our
velocity,
Or final. The question says final.
we are trying to find
Speed.
our
so we gonna make that
acceleration and
assume-
find the final speed. Okay,
No, we're about to.
unknown final speed.
Oh, unknown is final, I assume.
Now, to find that, right, we need to find the final speed. And we don't know the acceleration. Technically, but we found it.
We found acceleration.
Put it up there, put it up there. Because we had to find acceleration.
Okay, given. Put it
So
under
we can
given.
assume the what?
No. Put it actually we will put it as an unknown, and then now we have put it as assume. Only reason I say it's assume because we found it, and so we're assuming that it's the same acceleration for
That's
that
what we
motion.
calculated, right?
Yes. Because it wasn't given to us. We found it, right? So now we assume that we have the same acceleration because we found it from the first problem, right? But now we're assuming that the initial velocity is equal to 0. So now it is assuming that the initial velocity equals 0. In red, I want you to rewrite everything in the same colors that it is right now, right?
Mhm.
So rewrite the acceleration in green.
So it's
Rewrite the acceleration time in
initial
green.
velocity.
Yes.
Wait.
Rewrite the acceleration in the time in green. No, like on the what you call it? On the right, rewrite the whole equation.
Let's rewrite the whole equation. Okay, I get you. You're talking about rewrite this.
Yes,
Okay.
rewrite that. Keep what you
Black.
had in green. In
It was
green.
Okay.
Keep what you had in black, except for the initial velocity, which I want you to write in red.
Uh, 32.36 m per second squared equal to. You want the time in red, you said.
No, keep the time in green.
So final in black and then initial.
Correct. Yes.
0.15 seconds. You said final in black?
Final in black, initial in red.
No, like 0.
What is it?
Oh, it's 0, my bad.
There we go. What's the units?
It's meters per second,
Good.
not squared.
So now can we solve for the final speed? Now that we have
Yes, we
no,
can.
all right. So
But
now we
that's
gotta solve for it.
velocity, right?
Velocity, yes. And it'll be speed once we just get rid of the direction.
To BF over 0.5
One step equation, we're dividing, so we have to do what to solve it?
multiplied
There we go.
per second. Let me get my calculator.
So whatever you see division, you do the opposite. So you see how you see is divided, the VF is divided by a number. You see that, so you do the opposite. The opposite of division. is
I'll try and write
multiplication.
bigger, y'all. My bad. I'm not good at writing out boards. 32.36 times 0.15. And we get BF equal to 4.854 meters per second. That'll be the velocity final.
Okay, so we have the velocity final, our final speed, right? All right. Let's see what we got. Hold on. Yeah, that look about right, right?
You don't square that?
Yeah.
No, because this is not an acceleration. This is a velocity. Only acceleration is squared because it's per second per second. Correct?
Correct.
Did I do that right? Did I do the problem right?
You tell me.
So do we usually just use 3 significant figures?
I'm not gonna lie to you.
749.
I'm just worried about you
47.
understanding what's going on. I'm not pressed on say figs.
Oh,
Yep.
I'm gonna say right now, I don't.
I'm as long as you
Like, I
understand what's
understood
going on.
everything until we got to the, like, once we got past the 3 diagrams, so whichever one we did last time, whenever we had to do like the F apps, I think that's the one that's throwing me out. Because that's the applied force.
The applied force or just the part where you start doing like the math?
See, that's the part that I don't.
No, which one I'm saying, like the applied force, particularly like this, that specific force, or the part where you start putting in the forces and start doing the math?
Like this one.
Like this part, like when we got to, you see the part that's in green right here?
Yeah.
Are you good up until there, or are you confused after there?
No, I'm confused.
Just from that part, like the beginning part.
Okay, so like, I'm gonna take, soon as we got to this.
Right
part-
here. Circle on the board where you started being confused.
Okay. So if you just read the problem, I understand gravity because it's always down, right? So that's the only part I understand. When you get to this part, it's confusing.
That's more algebra. You were confused.
No, like this, like I understand this is the sum of all forces, which is mass times acceleration, so you gotta look at the problem, right?
Why is that though? Why are we using that one? Because it's another one where the sum of the forces is equal to 0. But why do we use that one for this one?
Let me look at the problem. Because it's accelerating,
Yes,
he's accelerating,
because he's doing what? He's,
moving
but how?
fast.
He's not just that, but like, what is he doing?
If you move
Oh, he's a
upward,
basketball player,
And he's doing what?
what is he doing when he moves up?
bouncing,
Bouncing off the,
bouncing off the rim,
but he's got to do what? He got to
jump,
jump. So he's getting off the,
ground,
and then to get off the ground, you have to do what?
accelerate.
Accelerate because you have to defy.
You have to beat what?
Beat
What do you
what?
have to beat what to get into the air?
Because what's pulling you down? You just said it.
What do you have to beat to get into
What is-
the air?
what is pulling you down?
force is keeping you down? That
Gravity.
You have, yes.
Gravity. So to beat, to jump on the air, you have to defy gravity. So therefore, you have to beat gravity. What
So then
happens
you
if?
have to overcome it, so that means the top is.
Hold on. What happens when you beat someone? You, like, if you beat them in a game, you
Win,
win. So that means if you win, the other one has to be
The loser.
the loser.
losing. So now underneath that, we have some of the forces equal to mass times acceleration. But technically, what does that mean? We have one force or a particular force that's winning versus another force that's
Lose.
losing. So in this situation, which force is winning?
The one on top, the applied force.
The applied force, because you're doing what? You're
I don't see, my thing is why would that be applied? Because when you say applied, I'm
What
thinking
are you
about
doing?
something.
wait. Jump.
What are you doing to your legs when you
Jump.
jump?
Hey,
What did you have to do? You had to do what?
You have to put some what?
hit the ground first and then jump.
Did
No.
you hit the ground force or did you what? You did
You
what?
just jump.
We'll do that again.
Yeah, I went down
you-
You
first,
bent your
knees,
It was-
knees, and then once you bent your knees, you what? You
bounce,
or P where you
Push off the ground.
push off the ground.
you pushed off the ground. And we said a force is a what? A push or a
Pull.
pull. So you bent your knees and you pushed off the ground, which in turn created enough force for you to accelerate your body off the ground and beat gravity to where you're in the air for a short amount of time.
Okay, so now that you say that. I
You
can
bending
see
your
it.
knees is storing potential energy. For
Yeah,
you.
Oh, we're not even there yet, but
Yeah,
yes,
please.
yes, we're getting it.
Like,
We're getting
hold
there.
up.
Yes. I like that. I like that. I like that. I like that.
Yeah,
I
because
like how
you
you
had
getting
my
there.
brain really scattered.
Wait till we get to that unit. We almost there.
Potential and kinetic energy.
But that's the part I did, like, okay, for instance, I just didn't understand these ones.
I'm
Like,
pretty
I
sure
don't know if
screens have
these are on
something to
the
do with
test,
potential
but this,
energy.
like, I understood
No.
this part.
No, it's gonna be that one right here. If you could solve this one, you could solve the problem about the
I
building.
can't solve this one. That's what I'm trying to tell you. I can do everything else but that one.
No, but
These ones. These is the ones I had a hard time.
that's the
with.
friction ones where we start playing
I
around.
had
It
a
was
hard
different, right?
times with these ones. I couldn't even.
Yeah, like I did it right here.
I could do the free body diagram, but I started getting confused when it's like, what do they mean AX, AY?
Oh, so like what we talked about. So like, hold on. Look at this one, right?
Mhm.
So you need that part, that beginning part. So you understand some of the forces, right? Now you have to understand that it's a winner minus loser. It's a one force is beating the other force.
Okay.
So in this example, like jumping, you have to bend your knees and beat gravity. So you have to apply enough force for you to get off the ground to beat gravity. And so that's what you're doing. And that's an applied force. So the applied force must be bigger than the force due to gravity. What is the force due to gravity?
It's 9.8.
It's basically your weight. So you got to be able to apply more force than your weight to get off the ground. Does that make sense though?
Yeah.
Like for
So
you
that
to
means I
jump,
have to overcome, like you said, gravity. So I have to be more powerful. I need more energy to
force
exert
instead
to
of
help
force,
push
yeah.
me up so I
Yes.
can stay for a suspended amount of time, however long.
Exactly, but we replicate that in math, right? So they tell us that the force that you applied was 3,222, right? And then that's going to beat your force due to gravity. And we figured out the force due to gravity, which is your weight, was almost 750 newtons, right? So that's literally
So what would you use to, what did he subtract with this?
right there to get that.
What's the number?
Take that,
9.8.
draw arrow right there.
So.
Oh, okay. See, I gotta see it.
No, yeah, right there. So that's what he did. So now he found that and then he put it in there.
Okay, I get
See the
that
next
part.
line? Write it now, write an arrow to the next line.
Write it down.
Right
Right
here
arrow.
to the next line.
So then you could see where he put, not there, to where he replaced it at.
This one right here.
This one?
One more up, one more up.
One more. This one?
Yeah, you replaced the
Okay.
graph with the number that you got.
Yeah.
Oh, 749.
Yes, he used that that's where that number came from.
It's
Oh, okay.
He found the
This was
weight
this was
times
the
9.8.
mass times gravity.
that was math times
Okay,
gravity.
so I get
and
that part. So
gives
that's
you your weight.
749 and the 320.25 is the newtons.
You bending your knees to jump
Right, but the 3225, that's the newtons, right?
that you apply.
Yes.
That's
But
the
also-
force.
too.
That's also newtons too, because that's your force due to gravity, how much you weigh.
So they're both your forces. So I weigh this.
Exactly.
This is kilograms.
Other
We
way,
do this-
pointing at. You said you weigh how much?
I weigh this much.
Other way.
I weigh this much.
Yes. And think about it. If you weigh that much, do you have to put the same amount of force or more
More
force to
force.
get off the ground?
If you
If I
weigh
weigh
this much,
749.7, I
You
have
have
to put
to-
more force.
Yeah.
So where's the more force at?
Right there. The
Yeah,
there you
320.25.
that's the winner and that's the loser.
So
And
that's
you
the more
subtract,
force.
And then you get 76.
Hold on. You subtract it and now you get your net force, which is what?
76.
Oh, no. You get your net force, which is what?
This.
Because what is 322.25
See that
minus?
marker? Because when I write this down, I just want to make sure so I don't forget. This is the net force.
Underline it and then point to it. Underline it. That. Where'd it come from?
This.
No,
No,
this.
this right here. 3,225 minus your weight is the net force.
Oh, I think I see what your issue is math. Your issue is math.
She's
Because you're getting confused at the fact that the equal sign like that's on the other
So
side.
this one don't count.
No,
That's-
it's basically a
That is-
simultaneous
it's from
equation.
here. It's literally from, you see the equals MA? This is your mass and that's the A.
Okay.
So it's like the left side
In the right
is
side
saying one
equation.
thing, but the right side is also saying the same thing. That's what we're saying with the equal
But you
sign.
only care about
This side.
A, not necessarily that side. You care about getting this by itself.
And you're
what-
using the left side to help you
What
find it.
order of operations do you have to do to get A by
Oh, that's
itself?
whenever you divide.
Yes, but before you get that, you have to do the left
See,
side
we
to
did
figure
it.
out what the number is.
We brought 765 or 76.5 over to this side. Now A is by itself and 76.5 is underneath dividing
And then we
240.75.
multiply.
No, you don't multiply.
This one you divide it because you see
Oh,
multiple.
yeah, I see he already divided. That's why in my head I thought I did the opposite.
This was multiplication.
Oh, yeah, this was already divided.
So to get A by itself, what do I have to do to this multiplication to get A by itself?
I can divide it.
Yeah, so you
You
divide.
divide on both sides, so you would get
Right, so
nothing,
I
nothing
divided
but
on
A.
this one and this one.
No,
Yeah,
Oh, yeah, yes.
because what happens is now
It
it's
cancels
76
out on the
the
right
Cancel
side.
out, and that's whatever the answer is. which
Yes.
is This.
Yep.
Okay.
But you're gonna need a calculator and stuff to get that
Yeah, I
answer.
got that part. See, it's just certain stuff. If I see it and I do it, it's easier. But it was just the part that we did last time that I was honestly really stuck on is the friction.
because we kept switching because it was sometimes it was the same, sometimes it was
Yeah,
different.
that's the part that really just.
But you always stick with that equation. When you know it's unbalanced, it's forces equals mass times
So what's the
acceleration.
WL? Wing times lit?
Winner,
Winner versus.
Oh, winner times loser. I
no,
thought that was
winner,
width times
winner,
length.
winner,
minus.
minus loser.
Winner minus. let me see.
So whichever, it doesn't matter which order, if you put the top one above the bottom one or the bottom one in front of the top one.
I got the math part because that's always easy to figure out. I just thought that right there was width times length first
Nope,
of all.
It's
Winner minus
winner
loser.
minus loser.
I was
So
over here going crazy.
the sum of net forces is the same as winner minus loser.
Okay.
These two things are the exact same thing right here. To get the sum of net forces,
Now
you
I have a
to-
question, Professor. When you draw these diagrams, is this the part that can honestly throw you off? Is this part, whenever you draw them, if you do this wrong, you're pretty much gonna mess up the problem, right?
Yes.
Yes, you need to
That's what I
know.
was saying. That's what what I was struggling with. And the friction is trying to figure out all the forces because sometimes I might think it's a force, an extra
Oh,
force, and
that's
it's not.
just, that's
So
just
I'm like, is
memorization.
it
It's
always
hard.
gonna be minimum 3 forces or are we ever gonna have 4 forces?
Some-
Trying to
Sometimes it's two,
generalize, you
sometimes
can't
it's
generalize
one.
it. You gotta
That's what I'm
just,
saying.
you gotta look at the problem. You can't generalize it.
Can't generalize it.
All right,
But
real
think
quick.
about-
Lakshmi, I know you're still there. What were you about to say? Because I wanted to point out.
Now that we've gone over the whole thing, I don't have anything to say. I figured it out. I just like skipped a step because I just thought since it's the, the net force, I just used the velocity that, or not the velocity, I didn't do the
Oh,
like
don't erase it.
initial final. I just called it velocity and
No.
used like,
Okay,
Yeah.
no, you're fine. I thought you were about to point out something. So now, this technically, right? That A, right? That equation is the what? What type of equation is that?
it's
Just
like
to
the
clarify.
definitional one, right? Like the
Exactly.
basic.
We use the definitional equation. But what did we cover at the very end of unit 1?
Kinematic.
The kinematic.
Kinematic equation. So now let's think about it, right? We use definitional equations to figure this one out, but could we also use kinematic equations?
Yeah, I just like my mind just automatically goes to the basic equations. 'Cause
Oh, it's good because you could walk yourself through it by talking through it. Wait,
that's-
I have a time and I have acceleration. I need to find my final velocity, but I know acceleration is equal to the change of velocity over time. And I know that the change of velocity is really just my final velocity minus my initial velocity. So then if I just find my initial velocity, I could find my final velocity because I have to find it. Now, what would be the initial velocity? Oh, wait, I got to start on the ground first. So if that means my velocity is 0. So then my initial velocity is 0. I can just plug in 0. Now I can find it, right? But now if you know all of that, right? Imagine if you knew the kinematic equations by heart to where now you're like, wait, I'm just looking for final velocity. I know that my final velocity is equal to my initial velocity plus acceleration times delta t. So now you just did all of this, but just in one step.
Right. And this
remember-
time it just turned out that the answer was the same, but if the initial velocity wasn't 0, it would
Yeah,
be.
this
It's a
is
lot faster, the one step versus all of that.
Because you got to think about this, you got to put it in here and be purified when it's already here. Lakshmi, say what you were saying again.
I was just saying, like, this time the answer was the same, like, correct, even if I didn't consider the initial velocity, but if the initial velocity wasn't 0, it would be wrong.
If the initial velocity wasn't 0, you would still do the same process. It would just you would put in whatever it was.
Right. No, the way I did it, the answer would be wrong, probably.
What would
Or-
you do differently?
I don't know. Never mind.
Okay. Well, I'm just saying with this one, right? You could just put in, now you know the initial velocity is 0 here, right? And you found acceleration 32.36 meters per second squared. And you know the time 0.150 seconds, right? What's 32.36 times 0.150? Is it still the same thing?
Yeah. It is.
Yeah.
Printed out most of it, not all of it.
See, I got that right here. And
I skipped most of this and then I started, printing maybe from like here, describing emotional equations, because then it gets into the.
I just printed out today.
Because I can't remember all these.
You can do it this way, where you talk yourself through it, walk through it, plug in the
And right
numbers,
now,
or
he's
you can
up
do it
there
this way.
doing BF equal to VI plus A times change over T.
Yeah.
And that's the same thing as doing all of this. That is the exact
Yeah, that's what
same
I'm saying.
thing.
His way, that way's way easier.
but you
It-
see,
it
this
does-
is from
The
This-
first unit.
is from second unit to get us to final acceleration. But once we
That's
get the
still the second
acceleration,
law.
That's
yes, this is the unit 2 stuff we just learned, right? But this helps us to find acceleration to where now we can go back to unit 1
and use the kinematic.
and use kinematic equation.
finish the rest of the
Okay.
equation.
So that's how we go back and forth where it's all connected. Now we're really truly understanding motion.
But I have a question about this specific problem, right? Is this one tied into Newton's third law at all?
This one,
You said if you start on the ground and jump up, it's like Newton's law for
every action is a
There's the
reaction.
opposite.
So what's the opposite reaction?
the flip
I-
is not.
Yes. There you go. Now we're here, right? I definitely could cover this in 9 minutes, right? So we're all looking, right? We are on the very last problem. We are on the very last problem of this unit. Now we're at our end goal. I know for a fact, I'm not asking, I know for a fact everybody can solve this problem because you are capable and willing. Are you ready for me where I can erase this?
Yeah.
You good? All right. Now I have 3
Hold on,
people.
let me take a picture real quick, sorry.
Take a picture. Even if you're online, take a picture if you can see it. I got 3 people in person. I got some people online. We're gonna solve this problem before 7 o'clock. And then we out of here.
Okay. Okay, thanks.
All right. After this, we done. I'm gonna leave this up though. Because this time we're gonna start with the given and assume and unknown.
So we're given the mass and the time.
Also remember, you cannot grade
I
me
see.
on your math on the practice problem. Just wants to make sure you understand. Doesn't care if you get, slightly off answers.
Slightly off is like sig figs. Not completely wrong. That would be crazy. You're sending somebody to a different planet if it's completely wrong.
Okay, well, yes, that's to take someone into hell.
Yeah, we don't want that. But I need to see the method, right? Because even if you do mess up, if you know the method, then you can be like, oh, I messed up here and fix your own mistake. So let's go here, right? We're gonna read the problem one more time. During a football workout, 2 linemen are pushing the coach on the sled. The combined mass of the sled and the coach is 300 kilograms. The coefficient of friction between the sled and the grass is 0.8. The sled accelerates at a rate of 0.50 meters per second squared. Determine the force applied to the sled by the lineman. Same thing here. What's the first thing we have to do with this problem, right?
Declare a variable for what things we have.
Okay. So now with that, give me what's given. Yes, you can.
Please do it. We're on number,
2.
In that top left corner, tell me what's given. What did they give us?
okay, yeah, we're on number 2.
Is that right?
So we given the mass. Let me
And the
see.
coefficient friction.
Yep. We given the coefficient of friction. And we're giving,
Time and mass.
are we giving time? What are we giving?
We're given an acceleration, not a
There we go.
time.
So erase time and just
Yes,
put
For acceleration. Yep.
Put A.
All right. So now we're given that, right? So now we need to find, I don't want to keep looking at this little paper right here. We need to find
We gotta find the.
What's the
term
unknown?
force applied,
the force applied. So we need to find.
sum of all forces,
So what's the force applied? That's the what?
mass times acceleration.
Oh, out of those three options. Do we know the force applied?
Do we know?
No,
So it's in,
Unknown.
that's what we got to find, force applied. There we go. We got to find the force applied. Now,
4 minus
let's see. Do we have anything that we can, let's start right there. Let's stop right there before we go to our assumptions, right? Well, what's one thing that we can assume that's always present
gravity.
is what?
Not
Not
right.
really.
There we go.
Is that even relevant though?
It is. Put G. G is equal to that. Now let's think about it, right? Victory in green. Write the free body diagram. Now that we have our givens and a little bit of our known, we have our known and a little bit of our assumed. Let's describe the motion of what's going on.
That's the part I gotta pay attention to.
All we got to do is describe what's going on by the forces.
He's asking for a free body.
So what force is always present?
Gravity.
So we got gravity. So we got F grav.
F applied. But it said it's pushing. So will it be like
Think about it. What are we pushing?
pushing
Oh.
the sled?
Sled. How does a sled move?
It moves.
Okay. But across a
Surface. So would it be normal?
So it wouldn't be friction instead of applied
Hold on.
force?
in the vertical because it's applied on a surface, right? So with that surface, right, that means it's touching the
Normal forces when
Ground?
two surfaces.
ground. So for it to be on the ground,
Oh, zero.
it's at zero because something's doing what?
Counteracting gravity.
Counteracting gravity by pushing it up. Yes. So
So
like
this is
gravity's pulling
overpowering
you.
this.
Is it overpowering or
It's
is
not
it
overpowering.
No, gravity's overpowering because you're still on the ground.
is gravity overpowering? Because if gravity is
If
overpowering, you
gravity
go which way?
overpowered it, you'd be in the ground.
So it's balanced.
It's balanced.
Balance.
It's zero.
Yes.
Okay.
So you have a normal force that's balanced with. It's balanced with what?
That's balanced with what?
Zero.
No.
But it's
zero.
not zero though, right? Like
Some of the forces is
Some
equal to
of the
zero,
forces.
but
Okay.
normal force is balanced with what? The force due to
Gravity.
yes, and we see that on the free body diagram. The arrows
Okay.
are about the same length.
Right.
Okay, yes. So now we got. You said there's a force applied.
Yes.
Does it say which direction?
Uh,
It doesn't matter. Just put it in one direction. So you're gonna put it to the right. So you're applying the force to the right, which means we're pushing the sled to the right. Now, while we're pushing it to the right, there's some type of what force?
Friction.
Friction, right? Does it go in the same direction as the applied force?
No, it's opposite.
Opposite. So now we have to write friction on the opposite side. Now, let's think about it.
Would they be equal?
They would not.
You tell me if it's going to be equal.
That's what I'm trying to figure out.
But think about
They
it.
would
If it's
not be
equal, what would happen?
It'd
with
be
the sled?
zero. So it's obviously.
What does that mean? What does that
balanced.
mean?
What does that mean?
They're balanced if it's zero. So they're
No,
obviously-
not math wise.
What does
If
that mean
it's the-
emotion wise?
If motion wise, if they're equal,
It's at rest,
which means it's not.
moving, accelerating. There's no acceleration.
No acceleration is a better word. Yes, it's no acceleration. But right now, look at what was given to us. Do we have an acceleration?
Yeah.
So therefore, are the forces balanced?
No,
No. So therefore, which one is winning, do you think?
I don't know. Whichever one
Applied
is shorter.
or friction?
Which one? Applied or friction?
Which one
Applied?
we-
Yes, because it's moving still to the whatever direction we say. We have acceleration there. So which arrow should be bigger?
The applied
Applied compared to what's the other one?
friction.
Yes, there we go. So applied is bigger than friction.
Or you gonna turn me to your teacher. I'm not even good at math.
Take this one. Now we have the free body diagram. Now we need two things, right? We have, which is this will actually solve your issue right here, what you said, Sean.
Yeah.
We have forces in both directions, right? Up and down,
Up and down and
left and right. What do we usually call up and down?
Horizontal or vertical.
Vertical, or on the axis is
X. Oh,
Perpendicular.
perpendicular, which
X
makes it,
and
what's the other one?
Y. Yeah.
Y.
Yeah.
Which one is Y?
The applied and
Vertical?
or
Yes, other way.
Vertical is Y, right?
So now we say the sum of the forces in the Y, write
it's the-
that, write that. Sum of the forces, so F Y is equal to, now look at the free body diagram. Are they balanced or unbalanced?
equal to 0.
Because they're
Balance.
right balance above. So the sum of the forces in the Y are balanced by the free body diagram. So now we say the sum of the forces is equal to 0. Now, what does that really mean?
It's not moving up or down. It's simply on the ground.
It's at rest.
It's at rest, or it's maintaining a state of motion. No acceleration, which means that the top force is equal to the,
Bottom force.
which means my up is equal to my,
Down.
so write that. U is equal to D. That's when I usually write this. Underneath,
Top force is equal to the down force.
yes. So up is equal to down. That makes sense, right?
Mhm.
So now, what is up and what is down?
It's unbalanced.
No, what is up and what is down? What forces are up and what
Normal
forces
and
are down?
gravity.
Write them instead of up and down.
Wait, what?
The
Wait,
names
what'd you
of the
say?
forces that are up and the name of the forces that are down. Which force is pointing up
Normal.
and which force is pointing down.
Gravity.
So they're equal to each other. Now, do we know what the normal force is?
No.
No.
But do we know what gravity is?
We know what 9.8 is. Yeah.
Can we, or basically, can we find the force due to gravity?
Yeah. It's 9.8.
That's acceleration due to gravity. We
The
want the
force
weight.
due to gravity is
That's the
weight.
part that keeps throwing me freaking off.
You got to say it exactly like that. The acceleration due to gravity. Think about it. Acceleration due to gravity. 9.8 meters per second squared.
The force.
Acceleration is meters per second squared.
When we say force due to gravity, think
Newtons.
of newtons. Yeah. And newtons is your.
And that's whenever you add it all up.
Mass
The
times
numbers,
acceleration.
right?
this
Mass times
is the,
acceleration.
this when you see that E.
Hold up. Acceleration is of gravity is 9.8.
Yes.
The
meters per
force
second.
of gravity is the sum.
It's
Not
not
the
the
sum.
sum.
Nope.
It's simply your newtons.
You have to calculate it. Though force due to gravity is actually mass times
Acceleration.
gravity.
Acceleration due to gravity.
Acceleration due to gravity, which is gravity. So write this on the thing. Your weight, right to the side. Write it in red. Write it in red. This is the side, so you know. The weight is equal to mass times gravity.
Which is the applied force.
Nope. Mass times gravity. What is gravity?
Gravity is one
Acceleration due to
force.
gravity.
Applied force is another force.
Wait, I'm so.
What's the acceleration due to gravity? Just said it 3 times.
9.8.
So now, to find the weight of an object, you multiply its mass times.
9.8.
Now, let's think about it, right? Down is pulling us is our weight, which is the force due to gravity. Up is our normal force. Do we know the normal force?
We don't.
No.
So just write normal force again. No, to the left. Underneath.
Hmm.
But can we find gravity?
We can find gravity.
How can we
a-
find gravity? Take that marker right in the red.
So force
one
equals
second.
gravity equals weight, right?
We have 300.
Force of gravity is equal to weight. Yes.
We have 300.
Nope. Right underneath there.
Underneath it. Okay.
Nope. Right next to it. Set it equal sign. Equal sign. Equal sign. Under. Under. Normal force equals.
Equals
Yes.
300.
Nope. First, write what it is. Is equal to what? Mass times.
Mass.
Mass times acceleration.
acceleration.
Due to.
Gravity.
So right instead of A, right?
G.
G. So now we know that, right? So now we know that the normal force is equal to gravity, which means the normal force is going to be equal times the mass times gravity. So now we plug in the numbers. The normal force is going to be equal to, what is the mass?
300.
And what is gravity?
9.8.
There we go.
Wait, are we finding the weight? What do you mean the normal force? Isn't the weight the F?
The
graph?
weight is 300 kg.
And is not the weight equal to the normal force? Because we just established that.
Oh,
So it'll be 300
yeah.
times 9.8. Which is, I don't know.
They're balanced, so they're equal.
Exactly. We over on time, but we still about to finish. We almost done.
300 times 9.8 is equal to 2940.
It's what, 29?
40. Yep.
It's just 2,900.
So now the normal force is equal to what?
2940 newtons.
249.
No.
2000. God dang.
2,940 newtons.
2,940 newtons, right? Now, reflect that and put it in blue on the free body diagram. Just put equal, normal force equal to.
So gravity would be in? Okay.
No, it's just that's newtons.
Newtons.
Force is measured in newtons. All forces.
What?
Whether you have force applied, whether you have force gravity, is measured in newtons.
The unit for force is newtons.
I don't understand why he put that on the bottom.
What do you mean?
They're the same.
They're the same. I just gave it a direction because we have direction.
Okay.
All right. So now we're there, right? Now we understand that the forces are balanced in the y direction. But what about the forces in the x direction?
They're definitely not.
They're unbalanced.
Unbalanced. Past the marker to victory. Now, victory, go up there and write. Then when we have unbalanced forces. Hold on. Before you even start writing the forces, what is the equation for unbalanced forces in general?
Oh,
Now write unbalanced in front of it. On top of it, sorry. Or right above it, right unbalanced. Yes, right there. And what direction are we in? Are we in the y or the x?
we're in the X.
So put an x right on the subscript underneath the x, like underneath the y as a subscript. Sorry, right next to the f, put an x,
Right next to the F.
like a little x.
Oh,
All right, so now we look at the left and right. We got the x, right? So now, before we talked about up and down, they'd be equal, right? And this one, if it was equal, we would do left and right. But right now, instead of us looking at direction, we want to see which one is
Bigger than the other.
bigger than the other, or
Winner.
winner
Over those.
or loser. So which one right now? Oh, so now we would write it then as W minus L equals mass times acceleration.
Mass times acceleration.
Now, technically, by this diagram, which force is winning and which one is losing?
The applied force to the right.
Do you agree with that, Victor? Okay. So now instead of W, we're going to put F applied. And then for L, we're going to put friction. And that's equal to the mass times. Okay. Now let's looking at this, right? Let's start filling in some things that we know. Do we know the F applied?
No.
So leave it. So write it again, F applied, just regular.
so I can
Now-
change color.
Yep, change colors, find that green. The green should be somewhere. So keep F applied is red because we don't know it. And then do we know F friction?
No?
We don't.
So
We
leave it
know the
red.
frictional coefficient, but we don't know the friction.
Hold that thought. Do we know the mass?
Yeah,
Yes.
What is the mass?
300.
That in there.
Well, acceleration must be the number. Oh, no, acceleration would be
Keep going.
0.5.
Exactly.
The acceleration is 0.580.
Good.
80.
That's math. We can do that. So let's do that real quick. Then I'll find us our new ones.
Wait.
What's the answer?
Yeah, it's 300 times 0.580. It's 174.
Just 174?
Yeah. It's
Mhm.
174 exact.
Thanks.
Okay.
It's an expensive.
74 what?
I see the TI 84.
174 what? Units.
It's
Units.
in meters.
Hold on. What is that? Kilograms times meters per second square. You have a mass times acceleration, which is a.
Oh, yeah.
There we go.
Force, it's a new, my bad.
So now we there, right? Can we solve that to where we find F applied yet? Because we have what?
We have two unknowns.
Two unknowns, right? But is there another way we can find
Yeah,
the code with friction?
yeah.
Yes, by doing that.
Final velocity minus initial.
Not that exactly, but what did you say earlier, Sean?
The frictional coefficient, we know that.
They gave us mu. That's the friction coefficient, right?
Is it mu or u?
It's
Yeah.
mu.
But
Yeah.
wouldn't that be with the
Like
normal
MU?
force?
Yeah, like mu.
Oh, wait, hold on. What did you just say? We have the what?
Coefficient.
Coefficient of friction. What did you just ask?
Wouldn't that be with the normal force?
Did we not just find the? So the frictional force is equal to,
The coefficient times the normal force?
write that in blue.
The friction of forces is equal to the coefficient.
Times.
Frictional force is equal to mu, the coefficient of friction times the normal force.
Because mu changes depending on the.
So it's supposed to look like this.
Times normal force. Don't rewrite it, put it right underneath there. You don't know F applied, keep F applied in red.
So it's supposed to look like this.
Exactly.
Okay. So then it'll be 2940 minus
Not minus,
equals.
equals what? 2940.
No, we don't know the friction, so it'll be 0 equals.
Not zero, you're trying to find it, so it's unknown.
So just friction,
Equals
Thing we're not doing that.
2940,
Friction
Times.
force is equal to mu times force normal.
2940. It'll be times itself.
If we're
What's mu?
If we're finding
174.
friction, it's
No,
gonna be
what's mu?
normal times the-
Look at where it's
Normal
at.
times, not times no.
It was in the given, so that means they gave it to you in the problem. Write that in blue. Write that in blue.
So it's 0.800.
You hear Courtney?
So it'll be 0.800 times 2940.
Did you hear what Courtney just said?
No, we didn't.
No,
What'd she
say
say?
that again.
Write that in
It's
blue.
0.800
Zero, yeah.
times 2940.
0.40.
Is that what the normal force is?
That's what the,
Yeah, that's what it says up there.
Isn't that
2940.
29?
that's 2940, my bad. That's 2940, not 0.40.
Yes. That's why I say
What's the
big.
2,940.
Okay.
And that's equal to what?
I don't know. Hold on.
I got it.
You don't know what it's equal to, but what is it equal to on the other side of the equation?
174.
Yes.
What's the units?
Oh,
That's the
okay,
answer?
I took a
Hold on.
Sorry.
You gotta
Well,
solve it.
this one has no units. This one is 10.
Yes. So now, can we solve for the F applied? What do we have to do first?
Apply this.
We get 2352 if you multiply 2,940 by 0.
Can you explain something to me?
Yeah.
I don't know if anybody else in class was wondering, why do we put the 174 right here?
It's because that's one of the identified things.
Mass times what?
Mass times.
Acceleration.
Where is it?
That's the part that just
Yeah, right
messed
here.
me all up.
174 is the M
It's
times A.
math with you. It's two sides. It's a system of equations. So
Maybe that's what's jacking me up. It's two different parts to this freaking problem.
There's always going to be.
it's
two
because you're
different
looking at it
sides.
as you're like the left side is whatever and it's equal to the no, it's literally like if it's like acceleration equal to a number. No, we have one side of unknowns equal to another side of unknowns and we're just solving back and forth. So like yes, you just found that something is equal to 174, but that also means it's also equal to something else on the other side of
Other
we're solving
side.
right now. That's
So
math.
if you
That's not
were-
physics.
We found one side of it to help us find the other side.
Yeah, I'm gonna have to ask for help to the extra.
But it's math. That's not
just-
physics.
It's just
That's
algebra.
math. You're struggling with algebra right now.
Okay, maybe I do my math wrong, cause like when I do it,
You're just struggling. You're just struggling with seeing it. Like,
It's
'cause-
just algebra.
and it's not
It
probably
don't
not
feel
even you
bad.
doing the math wrong. I'm forcing y'all to write it both on each side to where you see that it's equal to each other. But you don't have to write it like that.
You don't.
You can actually just solve for one separately and then bring it back into a whole new equation.
You don't have to put it as equal to another thing. You can make it as two separate equations.
that's what I'm saying. I don't,
If that's
If
comfortable for
that's
you,
what works for
that's-
you,
then
do that for you.
yeah,
Like you don't have to do it like how I'm doing it. I only do it like this because it's like I learned it like this, so it's visual.
And
But
there
you
are
can literally
multiple-
write 300 times 0.50 equals 174, and then you could find the applied friction is equal to blah 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 blah, that number. Then you can reset all that into a whole new equation and do it set it equal to 174 instead of having it written like how I have right here.
There are multiple ways to do things, just like the Newton's second law versus the kinematic equations.
All right, so now we're here. So you got 3, 2, 5, 2, and then that, right?
We add, right?
Yeah, you
Because you see what? So you see subtraction, so then you
Add.
add. There you go.
174 plus 2352, 2526.
what's what?
2526.
Thank you. Is it in 25, 26
And
newtons?
it's Newton's.
So
yes.
what?
You should always be mindful of the unit you're using.
Because what did we just find? We found the applied
We found a,
Apply force,
yes,
and forces measured in.
2526. Yes.
mu. No, mu has no units.
No units, but applied
Force,
forces are measured in.
meters per second.
No,
Forces
forces are
in.
measured in
I
all
meant
forces.
Newtons,
Yeah.
Say it louder.
newtons,
There we go.
because that's Newton's first law.
It was first law, second law, third law, all forces. Yeah, there we go. All right, let's see. What do we get?
2526 is equal to force applied.
25, 26 is equal to the force applied. It's on the right.
26.
Didn't do all that work to be wrong.
There we go. Victory slides to the side. Okay, if you can see that, take a picture of that. I hope you followed us. We might have been blocking a little bit, but also too, we were talking it through. So if you could hear us, and to be honest with you, more important than finding the answer is exactly the discussion that we had. Talking it through to where we could figure out the answer to the problem. That's how you need to be able to do that. But unfortunately, you're going to have to be able to do that with yourself. So that's why you need to know the definition of equations. You need to understand what's going on. And then also just use regular logic to just say, oh, what's going on? Oh, I'm pushing this. This is moving. I'm going in this direction. And if you could do this by yourself so where you could talk yourself to an answer, then you have a good grasp of physics. But once again, this is the second problem on your final exam. So I'm not lying. This is it right here, bless you. Not
Let me
changing
see the
it.
picture.
But I want you to understand you had to start with what? You're given, assumed, and unknown. Look at what the problem gave you, right? And get into your free body diagram to describe how the motion of the problem is working, right? Then once you get in there and you see, oh, I have balanced forces. That's Newton's first law. So the number of forces is equal to 0. I also have unbalanced forces. So now that's Newton's second law. And you use what you know from the balanced forces to help you figure out for the unbalanced forces. We had to use Newton's first law to figure out what the normal force is. By doing that, we were able to find out what the the frictional force is. And then when we had the frictional force, we was able to find the applied force. So you're gonna, with these second law problems, you'll be using first law along to help you out. There might be some problems later on where you might have to use third law to help you out too, but it's really just that they all come in pairs to where you can figure it out. But this problem is not that difficult when you really just take it step by step. But if you understood this, if you were at least able to follow it to a certain point, then you're doing good for this unit. So that is the last part of this unit. And I hope you guys enjoy spring break. And I will see you on the following Monday when we get back. Adios.
Thank you.
Thank you.
No problem.
Practice problems every day, y'all.
I do have a
Is this
question.
thing?
A week from today.
A week.
Practice problems due a week from today.
Then I can
I'm
give
gonna
you that.
change. You can keep that. I'm gonna
When is
change
the
the,
midterm?
That's stop it.
Are you putting it on this weekend?